Okay, so let's say that we have a simple harmonic oscillator potential, and psi of x and 0 is given to us as 1/2 psi naught of x plus 1 over square root of 2 psi 1 of x plus 1/2 psi 2 of x, where psi 0, psi 1, and psi 2 solve the time-independent Schrodinger equation. So we know the spectrum En, and we know what these functions look like. Let's say we want to get a sense of what the expectation value of the position is as a function of time, whether or not that's a constant, whether or not that depends on time or not. And so let's maybe get a sense of the probabilities of getting different energies. So psi of x and t is straightforward, right? It's just 1/2 psi naught of x times the exponential part, which is e to the minus I En, which in this case is E0 times t over h bar. And so we have e to the minus I, it's h bar omega naught over 2, so we get omega naught over 2 t, because the h bars cancel out, plus 1 over square root of 2 psi 1 of x, e to the minus, this one's 3/2, so it's 3I omega naught t over 2, plus 1/2 psi 2 of x, e to the minus 5/2. So we get that. 5/2 omega naught for the frequency of oscillation. So if we consider the expectation value of x, we know that this is not a constant because the parity of the superposition is not fixed. In fact, we have, so if we draw psi 0, and the turning points are, I don't know, say there, and this is where the minimum of the potential is, then the wave function looks like, right, so it's oops, it's trying to draw an even function. Oops, one of my erasers not working, but so I'm trying to draw an even function about here, and not a great job, but then we're going to bend the other way, this way here, at the turning point. So that's an even function, and psi 2 of x is also an even function. So of course the turning points are different, they're further out, so something like that. And so I'm going to come up like this, and then I'm going to come like this and bend like that, and then repeat this on the other side. So if I can do that, it looks something like that. And then I'm going to start to bend at the turning point the other way. And that's an even function about here, about this value of x. And psi 1 of x instead is an odd function. So if the turning points are, it's greater than this value, but smaller than this one. So let's put them like that. And now I'm going to, of course, bend this way. And then here I'm going to bend like that, always toward the axis. And then do something like that. Okay, so this is a superposition of two even functions and an odd function. And so this quantity will actually oscillate, and we'll see oscillations at multiple frequencies. So we have a frequency that is the difference between these two, the difference between these two, and the difference between these two.